Hello, welcome to this video on vector databases. You must have heard of these words alone, vector and databases, and maybe both of them together as well. And this is something which existed for a pretty long time, maybe more than a decade, but it recently came into light because of large language model. Just simply put, a vector database is something which takes unstructured data or structured data and then it indexes it, or it just transforms it into a vector space, and then you can just retrieve it from that space. Sort of like if you store stuff in a drawer and each region is for a particular kind of items, and then you just go back to that location and then you can just get it back. Vector databases work on the top something like that. And it's interesting to note that this existed for a very long time. And in things like banks, where you want to detect maybe an outlier, some transaction which happened, which is not supposed to happen. And this is probably has some characteristics which is not normal, right? So if you group all the other transactions, maybe one you can just find is outside that, and then you can just spot that outlier. So this has been in use in uh, several fields. But it's only recently that, because of certain advantages, it's been used along with large language models. All right, let's look into that problem for a second now. So, a huge problem with large language models is that it has a huge problem with the context size. So, initial models like GPT-2 and all had a very small context length in the order of hundreds. And then that was not enough to even drop a large essay or something like that. And then later on, when GPT 3.5 and GPT 4 came, it got extended to 128K. But if you notice, GPT 4.0 models like that are very, very costly to run. And one of the primary reasons is the context length. There have been research going on to try to make the context length larger without so much cost and in infinite context length and a lot of things like that. But at the end, it's somewhat unnecessary that just to find a small amount of information from a particular chapter, you just feed in an entire book to the model, and just it's a lot of waste of compute, even if you manage to do that somehow in an efficient manner. So yeah, if you have a big context, that means it would incur you like bigger costs. And you can see that newer models like GPT and all have a lot of cost when compared to maybe some other way we can probably get it, because we are feeding in all of that unnecessary information to that model. So things like RAG, retrieval augmented generation, which we'll talk about in a later video, is something which works with the help of a vector database where you can just query and get things done. Okay, maybe that was a bit too much just to begin with. Let's try to break it down a bit more. So it's vector databases, right? So it's a sort of database. A database is something which you can just store information in so that you can take it back. It may be something like uh, if it's an e-commerce website, the list of users, what items they like, what items are there in their cart. All of these things are managed by databases. So in a social network, who follows who, and the list of users who are in my following, who follows me, etc., and all of that. That is stored in databases, right? So there's several types of databases. We won't go into depth about any of these. We'll just briefly skim through each of them. You might have heard about relational databases, so which you probably can make in something like Google Sheets or Excel. And the advantage is that it has a lot of security and integrity, in the sense that you won't lose that data that easily. It is exactly in a table, and then you can exactly know that it is in all of these particular tables. And there is a lot of other advantages like normalization, etc. But we won't go into that. You uh, can learn about relational databases if you wish. But this is the most traditional database which we generally use. And it's a tad bit slower in some applications, and that is the reason we introduced more kinds of databases for use in specific cases. There's also columnar database, which if you don't want to go row by row and you just want to return from a column. And there is document based, where it's very easy to make it distributed or like scale it horizontally. If you have a lot of data, you can just store it in documents and then you can retrieve it back from those documents. There are graph databases where you can just store the relationship between entities in that, and through these entities, without having to like list down everything, we can access each data element from another data element. There are many applications of graph databases also, and even there is something called graph RAGs, which are helpful in the space of LLMs. But before getting into all of that, we'll just look into vector databases. I'll also briefly mention something like a key value database, where all of these values are just mapped to one key. It's like a lookup table, and then we just have the key and then we just get the data. A lot of varieties of these databases. And of our interest here is vector databases. So simply put, like I said earlier, it just takes the content and it has something just called the embedding model. Don't worry about it if you don't exactly know what embedding model means. And we convert it into a vector embedding. So vector, if you remember, is just represented by like two numbers, right? So if it's in a 2D space, if the vector space we take is 2D, maybe it has like one x value and one y value. And this is like one vector, which is in this particular two-dimensional space. Let's say you have this space, right? And if you take any point in this, let's say over here, you can get the coordinates of that, right? So this is probably like 1 and 1, right? And this is a vector from the origin to that point. And we can represent different things like that here. Um, Maybe like another point over here, you can represent that. And this is probably uh, -1, -2, something like that. And we can get all of these points in this 2D space. So, but this can also be a larger space. So this is like a two-dimensional vector space, but it can also be like three-dimensional, right? In 3D, so that we might have something like X, Y, and Z also. But this can extend beyond three dimensions too. And in this particular space, we can arrange all of our data so that certain regions or like certain data elements which are like grouped together. For example, easier to visualize in this two-dimensional space itself. Let me redraw that for clarity. So if you have a two-dimensional space and then you have several vectors which are like clumped together in place and several other vectors which are here. And if you want to find out which, like if you want to find out, like let's say a blue vector, and then you just need to look up in this area, right? And now you have three options. We ran into three options here. It's like 1, 2, 3. So you just run across these three, we just iterate between them, and then you just find the answer. So this is just a brief, simplistic way of explaining what it is. Let me just get into more details. First of all, what is an embedding model, right? What is meant by embedding? I'll try to explain it using an example. So you might have run across this problem of iris classification. Otherwise, I'll just let you know quickly. So we have three classes of flowers, which is Iris setosa, Iris versicolor, and Iris virginica. And they have some certain characteristics. And that's the sepal and the petal. So the petal has its length, petal has its width, sepal has its length and width. You can see here the sepal width is pretty high for setosa and things like that. So one thing is if we plot all of these together, as you can see, we can easily form these clusters. There are several mathematical ways of forming these clusters, maybe finding a centroid point, checking the distances. If it's like too far, then it's probably in another cluster, things like that. But as you can visually see too, that if we have these clusters formed, we can just actually label this, right? And yeah, so there are algorithms like nearest neighbors, etc., which we can use to form all of these clusters. And once you have that, if you want to find out like if we have a particular length and a width, you can easily expect that, let's say if the length is 4 and the petal width is 1.5, you can say that it's probably iris versicolor, right? And that's what these models help in. So what happens in a vector database is you have a similar space like that. I'll give you a little bit, I'll give you more examples for that. But let me start from here, that you have the space and then you have all of these areas. So if it's a 2D space, you can just think of it as curves. And if it's like a 3D space, maybe there are like small cubes or cuboids. And then if it's a multidimensional space, then an appropriate way to group a certain region in the vector space. Okay. And these we can call as buckets. And for a very simple example, let's say if you have a drawer, let's say you have a drawer, okay, and you have several regions. So maybe like this region you reserve for keeping jewelry like chains or something, and here you're keeping all your money, and here you're keeping something else, and you have all of these regions, right? And this is like in a 3D space. And, and when you want to retrieve something, that means that if you want to retrieve some jewelry and you know that it's in the top left corner, right? So if you probably put a coordinate system here, let me use another color there. So if I put a coordinate system here, and that is, let's say this is Z and this is X. Okay, so it's probably, and this is 0, 0. So if it is in this region, then it's closer to the origin, right? So all of these vectors, it's grouped together. So we just have to search in this particular region. Likewise, in this, if we can locate the bucket, which is like approximately near the target, then we can just search within that bucket and find out what our query is, or like what data element we have to retrieve. All right. So let me try to give you some more examples of embeddings. You might or might not have heard about the MNIST dataset. All right. Like the MNIST dataset is something which just detects handwritten digits. Like I could be writing this two or this two, any of this two, and it needs to detect this as two, right? And that's what the dataset goal is, like to have a data set of all of these handwritten digits to try to classify it correctly. So if we when we run such a model, what the model in turn does is it tries to group all of them together. So this is in 3 dimensions, okay? And it might be a bit confusing. Okay, what are we looking at exactly? So it is kind of a representation of how all of these values are kept inside the model. As you can see that all of these ones are together, and this in 3 principal components. A quick guide into what a principal component is as well. That if you have all of these original coordinates and then you have data only at a particular region, we don't need to take it absolutely right. We don't need to say, okay, we don't need all of these regions. This is wasted. So what we instead do is we change our perspective, right? So we change our perspective so that it's mostly symmetric and all of the data points are aligned better to the axis. So we just have all of those principal components. You don't need to worry about what a principal component is for now. But look at this visualization and understand that all of these values, let's say nines and fours, are somehow, when we take 3 principal components, all of these are somehow aligned together. But maybe when you look at even more dimensions, if it's not just represented by three dimensions, if it's represented by even more, then probably um, these fours and nines will separate in some other particular dimension. But if you just make it very simple, let's say I can take off another dimension from here, and now it's two, right? All of these ones are clearly easily separated, but in the three we have two also. But if I add this other thing, maybe three and two is separated better. So the main idea here is that all of these nines are stored here, and probably if you want to look for a nine, it's not that difficult, as in we don't have to look through all of this data. We look at this particular region and then we search through that, okay, which is the exact nine I want. Okay, these are examples of numbers and images and all of that. I also actually want to give you an example of an audio embedding. As you can see here, yeah, as I can scroll through this, I can see that all of these things are similar to each other, and all of these sounds are similar to each other. And this group using all of these characteristics of the audio, right? The frequency response and um, the spectrogram values. And that is how this clustering is done. So you can cluster any kind of data. It can be unstructured data, it can be structured data, all of that. You can just put it in an embedding and cluster things together so that you can just access them more easily and more efficiently, that we don't need to look at all of the other data. And one more thing I want to talk about is this hidden state. In our previous videos, we've talked about how we have an encoder network and then it creates a middle representation, right? The encoder encodes whatever input we give into this middle representation. And then the decoder does something. So this middle representation is always something which is interesting. It is sort of an understanding of that data. So if you can tap into that, then it's really useful. So that is something. So this particular encoder decoder network can also be used for just an embedding, right? And even before, when we were talking about word to vec models like word to vec, like simple NLP models, they still help in encoding some kind of information. Like let's say, for example, once we have an embedding out of this, we have things like words like king and man aligning together, and even maybe something like king and queen aligning together. And if you subtract the vector values of, let's say, so if you take the difference between a king and man and the difference between queen and woman, that would be almost the same. So you probably take the difference and then add to the other one, you'd probably get queen. Things like that. So these are vector values, and this is stored using this embedding model. And here, word2vec acts as the embedding model. And word2vec is a very simple, lightweight model, but you can also use heavier transformers for this purpose. There are several. Okay, this figure illustrates it slightly better. And another thing which I want to talk about is multimodality here. So it's not just images, or it's not just some text or music that can be accessed like that. A huge advantage here is that even things like videos or all of them together, and it can even link images to audio, right? The only way we could do that in an Excel table or something is if we have some kind of metadata, like you have the singer information, you have the composer information, you have the duration and all of that, you have that metadata, and then you somehow try to relate it. But you don't really take any information from the music in itself. But in this, you have the ability to do that too. So when we are talking about general intelligences or large language models, which are general purpose, multimodality, sorry, is very useful. As in, we can embed any of these, like even images, text, or audio, any of that, into vectors, and then we can store it in a vector data beam. And this is a huge advantage. There's several other advantages to, um, which is that it provides a very efficient long-term memory, and this was our primary goal too. That this is what we wanted. This is what we tried to achieve with vector databases recently, so that we can improve the long-term memory, increase the context without having the resource constraints. And another thing is it has some sort of a semantic search. It has some kind of an understanding of the underlying data. It's not just keywords, just like I said before, it's not just the author of a book. It's what mood is there in the book, what kind of a genre, or like even genre is a keyword, right? But the style of writing and things like that, even that you could have similar books. And just to recap, we have some unstructured data or structured data, and then we run it through an embedding model, and then we have it in a vector space. And we can just pick a bucket, which is like the most similar, and then we can search within that bucket and get whatever data we want back. We'll look into this in more detail in a future video, and we'll also learn how to use a certain kind of like a certain tool which is called Pinecone. We have several vector databases which are available today. Some of them are open source, some of them are closed source. Finecon is something which is quite famous. Literally, even Chroma DB is used a lot, VV8. All of these are used, but we will limit ourselves to Pinecone for now, and then we'll try to run a vector database and create a simple demo with Pinecone in a later video. Thank you.